皆様、大変長らくお待たせいたしました。ここからは表彰受賞者の皆様よりご講演をいただきたいと存じます。まずはじめに、栄養安全保障の向上を目的としたインド産トウモロコシ交配種に対する遺伝的栄養強化と普及と題しまして、インド農業研究所のヴィグネッシュ・ムトゥサミー博士にご講演をいただきたいと思います。So, Professor MUTHUSAMY, if you are ready, please take it away.
Thank you so much. Ladies and gentlemen, good morning to everyone. So now I shall be briefly presenting my significant research achievements in the area of genetic biofortification and dissemination of Indian maize hybrids for enhanced nutritional security. To begin with, I am born in the southernmost state of India, Tamil Nadu, in a village Pachakondan Valasu, to my parents, Mrs. Maragatham and Mr. Muthusamy Kaunda, and in an humble agrarian family. And after having my schooling over there, I moved to Tamil Nadu Agriculture University, one of the finest agriculture university in the country, and having a strong, dedicated motivation for research, I went to Indian Agricultural Research Institute, the premier institute for agriculture research in the country, to pursue my master's in genetics, followed by my PhD in genetics, where I started my research on corn biofortification. Since 2011, I joined Agricultural Research Service of Government of India, and I continue to work on maize genetics and breeding. Maize, as you all know, it's a crop with wide diversity and tremendous genetic potential, and it offers diverse end use as food, feed, and industrial applications. Given the crippling macronutrient deficiency like deficiency of iron, zinc, and vitamin A inflicting developing countries across the world, the Sustainable Development Goals focus largely on nutrition, and maize, one of the staple crop next to rice and wheat, is a potential tool to biofortify to address the issue of macronutrient malnutrition. To begin with, we started to biofortify maize for provitamin A since 2009. Initially, we screened a diverse germplasm for provitamin A carotenoids, where we could find a very little variation for provitamin A in the Indian maize germplasm to meet the recommended target dietary allowance. In the same time, at CIMMET Harvest Plus program at Mexico, Jianbing Yan and co-workers has identified a rare genetic variation in beta-carotene hydroxylase gene that could enhance the provitamin A in maize grain, and Dr. Jianbing Yan himself is an awardee of JIRCAS in 2010, and we immediately procured this improved germplasm from CIMMET, and we started our breeding program to introgress this favorable allele into our elite maize hybrids through genomics assisted breeding. In 3 years of time, we could develop provitamin A-rich maize hybrids that has as high as 21 ppm of provitamin A, and immediately we nominated this hybrid for national testing across diverse agroecologies of our country. After 3 years of rigorous testing for grain yield and grain quality parameters, this Pusa Vivek UPM9 improved was released by Central Varietal Release Committee of Government of India, the India's first provitamin-rich maize hybrid for commercial cultivation, which has high provitamin A, high lysine, and high tryptophan, besides higher grain yield. This hybrid is also the world's first multinutrient maize hybrid combining quality protein maize and provitamin A, which received wider attention in our country. Having success of Pusa Vivek UPM9 improved, we continue to develop a large set of provitamin-rich maize hybrids for diverse agroecologies covering across the country with continued genetic gain for grain yield. So we could clearly see now we have biofortified maize hybrids for commercial cultivation across all parts of our country. We have also tested the effect of these biofortified maize hybrids in the stakeholders like poultry and humans, where we have clearly observed feeding of these bioprovitamin A-rich maize hybrids to poultry birds has given higher body weight gain and has given greater feed conversion ratio, the important parameter in any poultry industry. Besides, when we tested these biofortified maize hybrids in humans, we could see these hybrids could meet around 60% of RDA of provitamin A. Not only we ended in development, we went for commercialization, where first we have given large-scale demonstration across different parts of the country under a Department of Biotechnology sponsored network project, DBT Kisan, where we have undertook large-scale seed production, and we have went for demonstrating in farmers' field, and also we did the extension through different government machineries and also through Ministry of Agriculture and Farmers' Welfare. Most importantly, considering the potential of these biofortified maize hybrids, several private companies come forward to license these hybrids, and around 57 licensing has been signed to 30 seed companies, which generated revenue to the institute worth of $172,000. And these companies are now actively involved in seed production and sale of these biofortified maize hybrids across the country. During the process of development of biofortified maize hybrids, we have seen that these hybrids, they have recorded as high as 21 ppm of provitamin A during the immediately after harvest, whereas after storage for a considerable period of time, it got reduced to only 8 ppm. That means the degradation of this provitamin A during storage is a major concern before it reaches the consumer's plate. To address this, first, we have screened that we try to understand the reason for this degradation, where we could see in the initial 3 months of time, there was a drastic reduction in the concentration of provitamin A, but the hope we got here is there do exist some genetic variation for retention, and we do got some genotypes that can have better retention when compared to other genotypes, and these genotypes now serving as a better source for our future breeding program. Further, we went to identify the genes responsible for this variation in retention, where we could, through gene-based expression studies, we could clearly validate this carotenoid cleavage dioxygenase gene 1 to be responsible for causing better retention. So, these high retention genotypes with CCD1 are our current target in our breeding program to develop provitamin A-rich maize hybrids with better retention potential. Further, vitamin A being a fat-soluble vitamin, we undertook to develop high oil-rich multinutrient maize hybrid with twin objectives. One, to increase the bioavailability of vitamin A in the biofortified maize, and number two is to provide high-energy diet to the poultry and piggery, which are the largest stakeholder of maize in our country. So here we have combined 6 genes for high oil, better fatty acid profile, and high provitamin A, higher tocopherol, and high lysine and tryptophan in a single hybrid. And this multinutrient high oil maize hybrid is in advanced stage of national testing. Further, now having high oil multivitamin A rich maize, now our target is to work upon lipoxygenase gene, which causes rancidity in maize, so that we can develop a comprehensive and holistic hybrid which has better retention and less rancidity for the benefit of both farmers and the consumers. Further, for the improvement of kernel iron and zinc, we followed indirect approach because the iron and zinc are polygenic in nature and they are governed largely by genotype environment interaction. So we targeted to introgress the low phytate 1 gene, which reduces the phytic acid, the major anti-nutritional factor that reduces the bioavailability of this iron and zinc in the body. We tried to combine low phytic acid with high lysine, tryptophan, and provitamin A. Thereby, we can develop multinutrient-rich maize with better nutrition and higher bioavailability. We sourced these low phytate maize inbreds by Dr. Victor Raboy from USDA, the father of low phytate breeding in the world. And initially, we developed gene-based markers for its utilization in the marker selection program. Then we went on to develop a series of low phytate-based maize inbreds. And these maize inbreds had reduced phytic acid, higher inorganic phosphorus, and better yield potential. And we have developed and released PUSA Biofortified Maize Hybrid 7, which has low phytic acid and higher nutrient for its commercial production in the country. Similarly, we have also developed low phytate 2-based QPM maize hybrids, where we have reduced the phytic acid, we have enhanced the inorganic phosphorus, and we have seen the better yield potential. And this hybrid PUSA Biofortified Maize Hybrid 8 is also released for commercial cultivation in the country. For the first of its time in the world, we have combined the two mutants, LPA1 and LPA2, to develop novel double mutants, and we have established their potential to reduce the phytic acid, and we have sanitized and developed agronomically superior inbreds, and these inbreds, these double mutant inbreds, which are novel across the world, are now being used for the breeding program to reduce the phytic acid in maize grains. These efforts on maize biofortification has led to several peer-reviewed international good publications, and I am proud to share my institute ranks top in having higher number of publications in the area of crop biofortification, and I am also one of the leading authors having largest number of corresponding author papers in the area of crop biofortification in the world. All this could be possible because of a strong guidance and support from my mentors, Dr. Devendra Kumar Yadava, my MSc chairperson, and my Dr. Harikishankar Gupta, my PhD chairperson, and Dr. Firoz Hussain, and my program leader at IARI New Delhi, for who inculcated in me the interest, the team spirit, the dedication to work for excellence, and to work with a hard dedication, because of which I could stand here before all of you as what I am today. With this, I would sincerely thank my organization, Indian Council of Agricultural Research, and my institute, Indian Agricultural Research Institute, New Delhi, for providing a wonderful platform and strong motivation to pursue my research on crop biofortification, and Indian Institute of Maize Research, Ludhiana, All India Coordinated Research Project on Maize, and our collaborators for active collaborative support, and the funding agency for all the financial support to carry out this vast, extensive research work, and the donor institutes from across the world who provided us the donor germplasm for different traits, and my dedicated maize team back in India, all the scientists, students, research scholars, and staff, and my family, my spouse, Mrs. Abhirami, is here, and my family back in my country, and my friends and well-wishers, and finally to the organizers, MEAF, AFF, SRC, and JIRCAS for a wonderful being host here. So with this, I sincerely thank you one and all for your patient hearing. Nandri, Dhanyavad, Arigato gozaimasu. Thank you so much.
Professor MUTHUSAMY, thank you very much, and Dhanyavad, thank you very much. ありがとうございました。それでは続きまして、農業・養殖・畜産における人工知能の研究とその国際的応用及び展開と題しまして、マチャラ工科大学のイヴァン・エドゥアルド・ラミレス・モラレス様にご講演をいただきたいと思います。So, Professor Morales, if you're ready, please.
Okay. Thank you very much. Hello. Thank you very much. Thank you. Artificial intelligence is an exponential technology. This technology can change the way we produce everything. In scale, in agriculture, our path is just in the beginning. In other industries, we see how artificial intelligence is changing the way they produce industrial processes. I hope in this lecture we can learn together how to use better the artificial intelligence for the agriculture. This technology must be used for the good of mankind. I am a technology enthusiast. I have training in agriculture, livestock, and aquaculture, but when I went 30, I studied my PhD in computer science. These studies allow me to try to connect both worlds, the world of technology and the world of agriculture. These tools include algorithms, sensors, computer vision, LLMs, and this technology helps to make decisions every day. I am a son of a poultry farmer, and in farming, you have to take decisions, but not always you have information to take good decisions. That's why I believe this technology can change the way we decide, the way we produce food. In 2011, I joined JICA course in Japan on endogenous development. I feel deep gratitude for the people here in Japan. The course taught me community-centered development, which means building technology with the people who uses that technology, and not only for the people, but with the people. We listen first, we prototype, and then we verify in the field. This mindset keeps us practical and focused on the results. Let us think about the opportunity for agriculture. Gordon Moore described the computing capacity doubles every 24 months. For farming, these are good news. We are still on the rising part of the curve, so we can digitize the farm and bring useful analytics closer to the field. As costs go down for the technology and devices improve, small farms can have that technology on their production. AI is not just a new trend. Since 1960s, there have been high hopes and also slow periods. In the past, limited hardware stopped progress and some ideas arrived before time. Today, with more computing power and more data, machines can learn from experience and support better decisions. In the field, we still choose the right tool for each problem and keep one foot on the ground. 3 ideas to help us understand AI. Artificial intelligence uses techniques that let machine mimic part of human behavior. Machine learning is the area of AI that uses statistics so systems improve with experience. Deep learning is a part of machine learning that trains many layer computational neural networks, and now this is feasible thanks to the computer science. Computers have learned to see very well. They can find objects and patterns in image and video. This gives us eyes on the farm with tools to check health and to count and measure animals and crops. Computer vision can turn a smartphone into an instrument to take decisions. When AI works with sensing, robotics, and connectivity, we get precision farming systems. These systems are standardized, rich in useful data, and ready to guide decisions. Simple protocols for light, background, and angle help a smartphone behave like a scientific instrument. With our collaborators in our research group, we implemented several prototypes and several projects. You can find the DOI in the slides, and we're welcome for replication and feedback. The first project we developed was about early warning in egg production using supervector machines. We aimed to detect when the eggs drops 5 days before the drop. So we'll let the signal into a forecasting for forecasting when the drops comes to the farm. And this was using a technology which is basic, supervector machines. It's like statistics. The second project examined near-infrared spectrometry in the sugar industry. We improved calibration across processes, which made real-time calibration control more reliable. The key was to standardize samples and protocols, and then they apply machine learning for better calibration, transfer industrial plants, gain speed and consistency without expensive equipment, using just machine learning to calibrate these instruments. The third project examined near-infrared spectrometry in the eggs farming tool, but we use a low-cost spectrometer, a spectrometer of about $500. It's very cheap, but it can be used with a smartphone connection and artificial intelligence like a tool for measuring how is the age of eggs. You can see the signal of storage time in the graph. The fourth project was similar, but in this case with milk. We use raw milk, and we tried to develop using CAN-nearest networks and a low-cost neurospectrometer to detect mastitis in milk, but without chemicals, using just light and a spectrometer. This is also published. Another tool we developed, this is not published, was in banana production. Banana has some disease that can be seen from the air. We use drones to detect some of this pattern in the leaves, and this can be applied. This can be applied to other crops. But I want to talk to you here about one development which becomes later into a startup. Using computer vision, we weigh and measure shrimps. In some settings, we reach 99% of precision, which is faster than manual work and produces less stress for animals. We treat the smartphone like an instrument, and using this technology, we can measure the length and the width of each animal, and we can calibrate with weights to know and detect each animal weight, and we have some statistics about each animal. We can have histograms of weight, and we can take decisions about the nutrition of the smallest animals just using a smartphone app and an application. This is why we founded a company which is called Larbia, which is precision biometrics in shrimp production. We try to reach shrimp farmers to aquaculture 4.0 in Ecuador, and we are in other 17 countries in just 5 years. We add new modules, and we try to make this technology available for everyone. This was the traditional method. This method was slower, 90% accurate, and just counted animals. They use a syringe to count each one by one, and it's time consuming and has a lot of errors, and it's not reliable. And using artificial intelligence, we developed a method which is 10 times faster, 99% accurate. It weighs, detects length, pigmentation, uniformity, condition factor, geolocalization, and it's real time. And you can have, using this information, a business intelligence information to take decisions. These are some decisions producers take using this technology. In just 4 years, they reduced 3.7 days the time they need to reach the weight. 3.7 days are more money for the farmers because they have more cycles for the same pond. And using this technology in a big company in Asia, they reduced 1.5 days the time they need to reach the weight. 1.9 in just 3 months. That's a proof that just the implementation of one technology can change the time, 1.5 days from 15 days. That's 10% of improvement. This technology allows also to have parameters like oxygen, pH, and having all that information merged in one place, you can take decisions like mining all that data. Now we have 2 million analyses in just 5 years. Some guided information is we took 4 years to reach the first million analysis, and we took just 1 year to reach the second million analysis. So this technology is growing very fast. These are some examples of how the detection is done. The detection is done by detecting each animal. You can scan the QR, and if you scan the QR, it will reach you to the website where is each sample. In the first image, you see small animals, small larvae. The second image are bigger juveniles, and the growth animals are in the third image. Here we have all the production chain in one graph. Producers can have all the information and check for improvements and detect which is working in the best stockings. If you detect what is working in the best stockings, you can take that decisions you take in that stockings and reach to the less productive stockings. we have traceability end-to-end, and having all that information in one place is valuable. How we believe it could be used in the future, the rise of LLMs is a very exciting field. We believe that having all that information, we can train a smart LLM, but having all the knowledge of aquaculture to have this information in one cell phone. I have 5 take-home messages. These are: digitize now, from paper to cloud; standardize or not AI, from prompts to agents; eyes on the farm; and apply science, it's not a hype. These messages, because of the time, I cannot read all of them. These messages is the core of we believe artificial intelligence can change the way we produce food. And we need more researchers and companies working on agri-food and on AI. We are open to collaboration in research, and we also welcome feedback. We want to thank JIRCAS, AFFRC, and my home university, and Larbi and my family, and the Embassy of Ecuador for the support. And I want to finish following a Japan Kaizen spirit of continuous improvement. We believe that small daily steps guided by data and AI can help us to make better decisions and produce better food. Thank you very much. Arigato gozaimasu.
Thank you very much.それでは最後に革新的なエンセットの加工及び発酵技術に関する研究とエチオピア5地域への展開と題しまして、アルバミンチ大学のアディス・フェカドゥ・アンデタ博士にご講演をいただきたいと思います。Professor Andeta, if you're ready, please take it away.
Thank you very much. Of course, this is Adesu from Ethiopia, and my presentation focuses on an indigenous food crop which is grown in Ethiopia, and that's mainly focuses also innovative processing and fermentation technology and its deployment to 5 regions of Ethiopia. And at the end of my presentation, I will tell you why these ladies are smiling, you know. So they got something which is quite interesting. So my presentation focuses, like after a brief introduction, I will highlight the major problem and that of the scientific solution that we tried to address. So I don't want to go to the detailed scientific aspect because most of the issues are already published and it can be easily accessed online. So let's start with the geographical location of Ethiopia. Of course, Ethiopia is geographically located in Eastern Africa, and it's, you know, Ethiopia, it has like 12 regions, and Ethiopia, like we have over 120 million people. Of course, it's one of the biggest in Eastern Africa, and agriculture is the backbone of Ethiopia's economy. You know, over 85% of Ethiopian people, of course, they are mainly rely on agriculture. So that's a massive population, and as you know, coffee, of course, it's obviously originated from Ethiopia, and we are also a center of genetic diversity for several crops, including barley, wheat, and I can mention a lot. And one of the indigenous crop is inset, which is the subject of this presentation, is also an indigenous food crop mainly grown in Ethiopia. So inset is mainly grown in 5 regions of Ethiopia, specifically in central, southern, and southwestern parts of Ethiopia. So I will highlight what inset is. We call this plant like inset or false banana, and it's also considered as the tree against hunger. If you have this plant in your garden, you will not have, you don't have any food shortage for the next 3 or 5 years, you know. That's why it's considered as the tree against hunger. And the plant is also a climate resilient food crop. If you don't have rain for a year, for 2 years, the plant stays evergreen. So you can harvest it at any time of the year. And of course, surprisingly, in Ethiopia, we have over 25 million people that use it on daily basis, meaning that over 25 million people, they use it as like a staple crop for over these people. They use it for breakfast, lunch, and dinner, likewise. So the plant is also considered as a multi-purpose because of its multi-purpose nature. The other interesting thing about the plant is that we can have more than 200 kgs of edible product per plant, which is the highest yield in any crop. So, but how insect gets processed? How it gets processed? So, insect, as you know, it doesn't bear edible fruits like banana. So, instead of the fruits, the pseudostem and the underground part, the corn part, both of them are processed, fermented, and the paste is baked to get bread. We call it kocho bread. And the fermentation aspect is the most interesting and a bit complex as compared to any other indigenous fermented food. So, what are the key challenges to insect production as well as insect utilization in Ethiopia and beyond? And we don't have insect in Japan, we don't have it in Europe, we don't have it in other parts of Africa. Why? So there are some key challenges in insect utilization, and one of the key challenge is the post-harvest issue. Of course, it's labor-intensive. We don't have any modern processing tools for insects. That's why the processing takes over 8 to 10 hours, which is quite labor-intensive. Especially women are suffering with this job. So if you have the plant, if you want a food, you have to wait a minimum of 2 months just to get fermented, which is quite long for food. And the other headache is the post-harvest loss. We have on average 34% post-harvest loss as a result of poor processing and fermentation, which makes it one of the highest post-harvest loss in crops. So what are the scientific studies that we did so far? You know, we tried to study, we had several scientific studies, specifically the comprehensive survey to understand the food system. Also, the other most interesting aspect is the microbial ecology of insect, which microorganisms are responsible for insect fermentation. There are some desirable microorganisms, there are some undesirable microorganisms, but the challenge is that the relative abundance of the undesirable microorganisms are that it's quite higher than that of the desirable ones, meaning that it needs that's why it needs some long time. And there is also undesirable microorganisms like Clostridium, Enterobacteria, I can mention a lot. So it was the main headache for the intervention. So what are the innovative aspects of our work? What we did so far. The first and the most important, we call it the game-changing innovation, was the development of a starter culture, This morning from the chair, the president already mentioned about the soybean fermentation, which is quite interesting. The same thing, we developed and validated insect starter culture, like Lactobacillus plantarum and Heliconistics. We have a diverse lactic acid bacteria collections, and we came to know that insect is a lactic bacteria fermented ecosystem. Then once we understand that system, we tried to develop a starter culture. And it was tested under laboratory scale, field scale, then under farmers' condition. Then finally, we took it to the market. It's become commercialized, which is really interesting. And the most interesting part also, it reduced the fermentation time from 60 days to just 7 days. Within 7 days, you can have a very good premium fermented paste. And it also reduces the risk of unwanted microbial growth, most specifically the Clostridium, and we have a much improved quality, both sensory and the nutritional quality of the fermented product. And as you can see from this one, for example, is an inoculated insect with the it is like 2-month fermented one, we have variable sensory quality. We don't have a predictable fermentation as well. However, when we fermented with starter culture, we don't have post-harvest loss. Everything that comes into the container, it becomes a food, and with a much better quality and a much predictable form of. So with our starter culture, it's one of the game-changing innovation. We have several papers already published in AI journals, so you can find it online. And the second innovation was the machineries, you know. We wanted to design with the community, of course, as the previous speaker said. We tried to design a machineries, user-friendly and cost-effective machines. And the innovative aspect is that everything was produced, manufactured locally, and it was piloted. Then once we had a very good feedback from the farmers, then we took it to the next stage, which is mass production of the machine, which significantly reduced the workload of the women, You know, if we have 20 million insect growing farmers, they have been struggling with the processing. So it reduced the processing time from 8 to 10 hours, just less than 1 hour. So they can have the food product. It also reduces the food loss, like less than 2% from 34% of the previous one. And the third important innovation was also the introduction of a new fermentation vessel. They have been fermenting insect in a soil pit. Just they keep it in their backyard in a soil pit. So what we try to introduce a new type of fermentation vessel in a confined container, which makes it really quite interesting, and which also maintains anaerobic condition, and it also enhances the quality of the final product. And after this, the three innovation, we managed to have a brand new product to the international market, which is the Kocho flour. As you can see it, once we have the machinery, once we have the starter culture, we managed to have a brand new food product which is called Kocho flour. Traditionally, we have been using only the paste, the wet paste to bake bread. That's the only thing that we can do. But now, thanks to all this innovation, we managed to take the Kocho flour into the market, to the community. And what's unique about this food product? Of course, we received several national prestigious awards for this work. And the Kocho flour it's gluten-free, organic. Everybody loves organic food and gluten-free. And the most important, it's diabetic-friendly. It has low GI. And it's also nutrient-dense one. It's rich in calcium, iron, I can mention, and it's also rich in different micro and macronutrients, which makes it like really interesting. And it can be used to make cakes, waffles, we can make cookies. And the most funny part is that we established a startup company, and all these products are in the market in Ethiopia. So luckily, we have gluten-free and nutrient-dense food products out of this innovation. We took it from the lab to the market. That's how it worked. And now we are aggressively working to take it to the international market, which is the Kocho flour, multi-purpose Kocho flour, thanks to our innovations. And this is the summary, you know. This is, if we have the plant with the traditional system, we have to wait a minimum of 2 months to get the food product, just the bread. And with our innovation, within maximum of 7 days, we can have a premium multi-purpose Kocho flour for the local market. Can you believe the shelf life of Kocho flour is much higher than 2.5 years? It's shelf-stable product, and it's already. And next, what we did is that we tried to scale it up to across 5 regions of Ethiopia. So we have a successful, tested, validated technologies, and we have been training university graduates, TVET graduates, so that they can take this business into the. So we have over 42 pilot plants across 5 regions of Ethiopia. Each site, it's like a meal house. Each site supports a minimum of 3,000 smallholder farmers. They are direct beneficiaries. So you can imagine how many smallholder farmers are being benefited out of this business. It came from the lab to the market. Now they are taking it to the next stage. Of course, the farmers they are still smiling because they get something really interesting so they get safe food, nutritious one, and a diversified product from insect plant as a result of this innovation. Plus, women, especially in insect growing region, they have been the one who has been suffering for the last thousands of years. Now they get a source of income as a result of this innovation. They have diversified income. You know, yeah, they already had the craft business. They already had everything from this one. And we also enhanced the food and nutrition security. And finally, this initiative becomes a national program, a national INSET flagship program. I was one of the national grand committee, and last December, we launched a national flagship program. So INSET becomes a strategic crop in Ethiopia and beyond. Even we took it to Kenya, thanks to the Ethiopian government. So thanks, JERCAS, my host institution, Arbam University, the Ethiopian government, ICGAB, of course, and also Betin for their technical and financial support. Thank you all.
Dr. Andeta, thank you very, very much for your lecture. Thank you so much. さあ、それでは改めて3名の受賞者の皆様に大きな拍手をお送りください。それでは以上をもちまして2025年若手外国人農林水産研究者表彰式を終了といたします。会場にてご参加の皆様にはこの後少しご案内がございますので、もう少々会場内にてお待ちください。またオンラインでご視聴いただきました皆様、最後までお付き合いくださいまして誠にありがとうございました。